Okay, so this is problem 68 from chapter 26. So the problem is asking for the circuit shown in figure 26-18a, show that the decrease in energy stored in the capacitor from t equals 0 until one time constant has elapsed equals the energy dissipated as heat in the resistor. Now first of all, I redrew the figure on the blackboard, but the figure in the book is a bit misleading. Here they're using a short line segment and a long line segment here for a capacitor. That's the symbol, of course, for a battery. Now here the battery sort of acts like here the capacitor sort of acts like a battery, but it's still a capacitor. So they should have used the capacitor symbol. It's something like a typo in the figure. But this is the configuration we have. So we are going from t equals 0 to t equals tau, one-time constant, which is of course R times C. Okay? So this capacitor is going to discharge over this resistor, and we know what the behavior is going to be in this case. The charge on the capacitor is going to decrease exponentially with the time constant RC, and the current over the resistor is also going to decrease exponentially with the time constant RC. And this Q0 is going to be the initial charge on the capacitor. So because the capacitance is charge per unit potential difference, the charge is just a product of these two. So it is C times V0. This V0 is a little bit misleading. It's a potential difference, but I'll keep the notation of the book. And that I0, the initial current, is going to be potential difference provided initially divided by the resistance. So we started discharge and we discharge like this, and we started this current, and then we decrease our current in that following manner. So discharging occurs. Now we have to compare after one tau passes. We have to compare the energy dissipated in the battery in the resistor with the energy decrease from the capacitor. So they are saying that all the energy that's dissipated in the resistor is coming from the capacitor. Now, is this something plausible? Yes. Is this something that should happen? No. Okay? So of course, this has to come completely from here, but this could go somewhere else. Right? So these charges are also, coming and meeting the other charges on the other side. So there could be some heat dissipation on the capacitor itself as well, and they're saying that this doesn't happen. Okay? So what's happening here is that all the heat dissipation takes place over the resistive element, no dissipation on the capacitive element. All right, so let's check this out. We're going to start with the resistor. All right. So I'm going to calculate the total energy change over the resistor, and because this depends on the current and the current is changing, I cannot do this in a single shot. I have to calculate the energy dissipated at each small time interval and add these up. So this is going to be some integral of t from equals 0 to tau. How do I write this in terms of time? Well, the definition of power is dE by dt. So this becomes P dt from 0 to tau. Okay? And the power for resistive circuits is I times delta V. This is not very useful because both of these are changing. And in fact, I've already written down how I is changing. Let's write down this in terms of current and resistance. So this is going to be I square times R. So I can actually get an expression for power. Okay, so let's do this. So this is going to be from 0 to tau I square R dt, and I square, this one here, is going to be I0 square e to the minus 2t over RC dt, and this is from 0 to tau. This I0, there's also an R term. This I0 can be taken out, it's a constant. This R can be taken out. This integral can be done, it's an exponential. So exponential of the integral of exponential itself times some constant. So this is going to be I naught square R. The coefficient here, we're going to need to reverse it. So minus RC over 2, let's put it this way, times, this is e to the minus 2t RC, it's the exponential itself, over RC evaluated from 0 to tau. Okay, so this is the primitive of the function, minus RC over 2 times e to the minus 2t RC. If you take the derivative of this, you introduce a coefficient of minus 2 over RC, which cancels this, and you end up with the function that you're trying to integrate. Now, I can evaluate this at t equals 0. This is just 1. E to the 0 is 1. At t equals tau, then tau is RC. This is e to the minus 2. Okay? So this one becomes I naught square R square C over 2. And what did I call this? E to the minus 2 minus 1. But there's a negative sign here, so this is 1 minus e to the minus 2. Okay? So this is the energy dissipated in the resistive part of the circuit. Let's calculate how much energy decrease has occurred over the capacitor. I'm going to erase this part. So the energy in a capacitor is a half C delta V square. Again, I want to write this in terms of Q because that's something I know how it changes, and the C is going to be a constant. So by definition, C is Q over delta V. So delta V is Q over C. So this is going to be a half Q square by C. So let's take a look at this. A half Q naught square e to the minus 2. Sorry. So we start with this. A half Q naught square by C. This is the initial one. The final value is going to be, if I introduce a t here, this is e to the Q naught times e to the minus 2. So this is a half Q naught square e to the minus 2. This 2 coming from squaring Q naught times e to the minus 1. And if I write this, this is a half Q naught square over C, 1 minus e to the minus 2. Okay? So it remains to be shown that this I naught square R square C is in fact equal to Q naught square over C, and I can do that by erasing this space here. So Q naught square over C is equal to, so Q is C naught, C square V naught square by C. So this is C V naught square, whereas I naught square square R square C is of course V naught square times. So these two are equal to each other, which shows that the energy change in the capacitor is equal to the energy change, energy dissipated over the resistor. Okay? This is a little bit messy, of course, the algebra is messy, but that's purely because of space constraints. You can make this a lot more cleaner at home. Do we have another thing? No. Okay, so that's all for this question.